Namaste. Our today's lecture is Hypersonic Equivalence Principle and Blast Wave Theory. Right. So far we have already studied about the hypersonic small perturbation equation, right? And we have derived and we have finally found that the this is applicable for the flow over a slender body and all those things. Now, uh, today's lecture is on hypersonic equivalence principle and blast wave theory. How we go with, right? We will see. Okay, I acknowledge the John D. Anderson's hypersonic and high temperature gas dynamics, right? Let us start the discussion of hypersonic equivalence principle. So, um, in the hypersonic small disturbance theory, we have derived a set of equations that we already know, right? Now, let us consider this equation. Say, um, so let us consider the equation for unsteady two-dimensional flow, right? So let us say the the equation for unsteady, right? First one is unsteady, unsteady. Then I consider it for two dimensions, right? Two dimensional. So I consider this two dimensional in YZ plane, right? YZ, right? So now we can write the basic equation, the continuity equation, x momentum, y momentum, z momentum, and the energy equation. So here I can write dou rho by dou t. So please note it is unsteady, right? Then dou by dou x of, sorry, it is in YZ plane. So it is in YZ plane and hence it will become dou by dou y of rho b plus dou by dou z of rho w. Okay, that is equal to 0. See, in this hypersonic equivalence principle, ultimately we want to say that the principle is the steady hypersonic flow, right? The steady hypersonic flow over a slender body, right? That we want to equivalent it to the unsteady flow over one less dimension. That is what the idea, right? So now we consider this unsteady 2D YZ plane, and we will compare this with the one which we have derived already, right? Steady hypersonic flow, right? So we will see how it works. So this is the first equation we have written, and then let us write the uh, x momentum equation. But we don't have x momentum equation since we consider the YZ plane. So let us go for the equation dou v by dou t, rho into dou v by dou t plus rho v into dou v by dou y. Please remember this dou t term we add because we consider the unsteadiness, right? Then rho w into dou v by dou z. So that is equal to minus dou p by dou y. Right? Now let us write the z momentum equation rho into dou w by dou t plus rho b into dou w by dou y plus rho w into dou w by dou z. That is equal to minus dou p by dou y. dou z, right? So let us write the next equation, right? That is the energy equation you can consider. Dou by dou t of P by rho power gamma plus B into dou by dou t of, oh, sorry, this is B by dou y, right? Dou by dou y of P phi by rho power gamma plus W into dou by dou z of P by rho power gamma. So that is equal to 0, right? Now we have a set of equation for unsteady two-dimensional y z plane, right? Now, as usual, we do in our discussion, right? In all our cases, we use to non-dimensionalize the equation, right? So let us non-dimensionalize this equation. So, so let us non-dimensionalize this equation. Non-dimensionalize these equations, right? Say I write this rho, this wave that is equal to rho by rho infinity, and V is equal to V by V infinity. Then W is equal to W by V infinity, and P is the pressure that is equal to P by rho V infinity square, right? And I write the time t that is equal to T by L by V infinity, right? You can also check it is dimensionally valid or, right? So y, I can write y by L. Similarly, x is equal to z by L. Now, we know that here V rho infinity, V infinity and all can be treated as the reference quantity, right? So let us now write these equations in this non-dimensionalized form. Now the equation can become, say this equation is now represented in non-dimensionalized form, right? Say dou rho wave by dou t plus dou by dou y of rho, rho wave and this v wave plus dou by dou z of w, that is equal to 0, right? Then let us write the next momentum equation that can be represented as rho wave dou by dou v by dou t plus rho v wave into dou v wave by dou wave plus rho wave into w wave into dou by dou v wave by dou z, that is equal to minus dou P by dou Y wave. Right. Similarly, let us write the Z momentum equation, that is rho dou W by dou T plus rho wave into dou W wave by dou Y plus rho W into dou W by dou Z. Right? So that is equated to minus dou P wave by dou Z wave. Right? Then let us come back to the energy equation. Right? So the energy equation we can write dou by dou T. Right? All you have a wave. So that is P wave by rho wave power gamma plus P wave by into dou by dou Y wave of P wave by rho power gamma plus W into dou by dou Z of P by rho power gamma. That is equal to, right? So we have a set of equation now, right? This set of equation is a non-dimensionalized equation, right? So this equation is non-dimensionalized. Right? Now, there are two sets of equations. Initially, we have a two-dimensional unsteady equation expressed in y-z plane. Here we have a non-dimensionalized equation. Right? So this is the first set of equation, and now when we non-dimensionalize, we have this equation. Right? Now, when comparing these two sets of equations, it is slightly of different symbol, but they are identical sets of partial differential equations, right? So, as you know, we already have the hypersonic small disturbance equation in the one hand, right? Say hypersonic small disturbance equation. We have hypersonic small disturbance equation in one hand, and see the you already remember that the hypersonic small disturbance equation is governed for the steady flow, right? It is for steady flow, and for three-dimensional flow, that is over a slender body, right? Over a slender body, right? So we have hypersonic small disturbance equation in the one hand, and in the other hand we have the non-dimensionalized equation by considering only the two-dimensional and unsteady flow, right? So now the set of equation looks identical, right? Say if you see the hypersonic small disturbance equation, right? I recommend you to visit that. So both these sets are identical, right? So we can say that these both are equivalent, right? So equivalence, and this equivalence between these two types of flow, right? So this equivalence is given as the a mathematical justification for the hypersonic equivalence principle, right? So, to read, I mean, I hope the hypersonic small disturbance equation you have already, right? So, we can write that the the steady the steady hypersonic flow over slender bodies over slender body is equivalent to an unsteady flow, right? An unsteady flow in one less dimension. One less dimension in space, right? Right? So the steady hypersonic flow over a slender body is equivalent to an unsteady flow in one less space dimension, right? So I hope you can also have a comparison, right? Only the notation may be different, but it looks identical, right? So we can define the hypersonic small disturbance equation, I mean small disturbance equation and the non-dimensionless equation which we consider here, right? Now let us say further, further we can consider in the equation that um, say x bar is equal to x by L, and that is equal to sin t, right? Say we can also write that t is equal to v, v infinity by L. So we should not simply equate, right? But x bar, if we can define in this way, then the t wave can be defined as t wave is equal to t. So there we have written something like this: t wave is equal to t by L by v infinity. I hope you remember, right? Yeah. Yes. Right. So now the point is we can write x is equal to, say, x can be equated to v infinity into t, right? So it is possible to establish a physical basis to show the hypersonic equivalence principle. So let us visualize a y-z plane perpendicular to the screen, right? Y-z plane perpendicular to the screen, right? Now a hypersonic body is moving at a velocity of v infinity, right? That penetrates into the screen. Please remember the screen is two-dimensional. The screen is two-dimensional. I assume that a hypersonic body is entering into the screen. It penetrates into the screen. Say it can be shown by this way. So this is a plane, that is y z plane, right? Say, let us say this is a y z plane. So you can see here, right? This is the y z plane. Now, um, so this is a three-dimensional body. Of course, it is a slender body, right? It's a slender body, right? And it travels with a velocity of v infinity, and the space is in x direction, z direction, and y direction. So the y direction is perpendicular to the screen, we can assume, correct? So YZ is a screen where this slender body is hitting this particular screen. Now, at time t is equal to 0, in the YZ plane, you cannot see anything, right? This is the pointed nose of the slender body. Okay, this is the pointed nose of the slender body. Now, let us say the next time step, time t is equal to 1. Now the slender body which penetrates into the YZ plane, right? Now the slender body penetrates into the YZ plane. Now when you take this particular plane, you can see this particular region is actually the body, right? And the one which is around is the shock wave, right? So we can represent this in this way. So at x1 is equal to v infinity t1, and this t is equal to t1, we can see that in this particular yz plane, we can see both the slender body and the shock. The shock is around, right? Now let us say x1 instead x2 or time t2, right? This is time t2. So x2 and this time t2. Now, what happens is it expands further, right? It expands further. So we can say that here the shock wave is propagating, right? The shock wave is propagating. So we can say that the trace of the body and its shock wave in the YZ plane. So here it is in the YZ plane. Do you remember we have studied the unsteady flow in a YZ plane? That is what the explanation here, right? So these three examples, three times t1, t2, and t equal to 0, which shows the YZ cross section where the slender body penetrates in, right? So you see here, this is the slender body, and then time t1, t2. So in YZ plane, the changing body shape, right? The changing body shape looks like an expanding cylindrical piston, right? Moving at a velocity, moving at a velocity v infinity, right? Say this, say probably the body, we can say the velocity wb, and the shock we can say it is ws, right? So the cylindrical piston moving at a velocity wb, and the cylindrical shock which is coming outwards with a velocity of ws, right? So we can say that due to the hypersonic equivalence principle, right? So we can say that due to hypersonic equivalence principle, the unsteady flow in the YZ plane, can say that due to the hypersonic equivalence principle. Here we can say that this is unsteady flow, right? Unsteady flow in YZ plane. The unsteady flow, in YZ plane. That is what the equation we have first derived, right? The unsteady flow over YZ plane at various times, right? At various times, say time is equal to T1, T2, T3, and so on, gives corresponding steady flow gives corresponding steady flow results in YZ plane. Means which is located at at x that is equal to x1, x2, and so on, right? So you can see the diagram in the right, it shows the YZ plane, which is unsteady, right? And here we can say that in the left side, this shows at the various x locations, x1, x2, x3, right? So hence we can conclude that the steady hypersonic flow, over a body can be constructed from an unsteady flow in one less dimension, right? Right. So here it is in 3 dimensions, and now we represent the same in the 2 dimensions. Here it is, right? So here it is 3D and here it is 2D. Right? So we can say that the hypersonic equivalence principle says that the steady hypersonic flow over a slender body can be constructed from an unsteady flow in one less dimension. Right? That is what the hypersonic equivalence principle. And correspondingly, we can discuss the blast wave theory, right? So the blast wave theory is almost like, in your in this case you have a body, hypersonic body, and the shock wave is propagating, right? So this propagation can be equated to a blast happened at a particular point and how the blast propagates, right? So that we will discuss in the further classes, right? So the propagation of shock wave due to the energy release and all considered as a blast wave, right? That we will discuss later. So the today's discussion is very simple. It is hypersonic equivalence principle, right? Thank you very much.